I would like to talk today about moduli spaces of bundles on Riemann surfaces. And we're going to apply to moduli space of bundles the kind of function theories we talked about last time. So but maybe I'll remind you when we get to it. So here's the kind of geometric setting we'll be talking about. We're going to have X is going to be a compact Riemann surface of some genus G. Or if you'd like, complex, projective. They're going to be smooth, connected, algebraic curve over the complex numbers. So we're something we draw like that. And so what are we going to look at for such a Riemann surface? The first object I'd like to discuss is the Picard group. Pic X is the collection of holomorphic line bundles on X. So this is going to be our first object of study. So what kind of structures does this thing have? First of all, it's a set. We can look at the set of isomorphism classes of line bundles. But in fact, it has a natural structure of an algebraic variety over a complex manifold. And that's basically because we know how to think of a family of line bundles. And we know how to parameterize families of line bundles in a nice way. So once we know what it means for a family of line bundles to vary algebraically, this gives us this set, the structure of an algebraic variety. And the second thing is that this is an algebraic group. This has a structure of a group thanks to the tensor product of line bundles. So these are kind of two of the key features. What else does this look like? Well, we have, if you have line bundles have a degree, which is, or if you'd like, the first Chern class, which is an integer. And so we have a map from the Picard to Z. And in fact, the Picard group of X can be written as a product of pic 0 of X across the integers, where pic 0 of X is the Jacobian. Maybe I'll go over here. So pic 0 of X, this is the Jacobian of X. And this is an abelian variety. This is an abelian variety of, as we discussed yesterday. And to write it explicitly, you can identify it in, well, we want to identify it as a vector space modulatus. I can write it as, look at the space of one forms on X, dual, so functionals on one forms up to functionals on one forms come, for example, from looking at homology classes on X. We can integrate one form on a homology class, so we get a functional on one forms. So this could be identified as C to the G mod Z to the 2G. So where G is the genus. OK, so this is a G-dimensional complex torus. Hopefully everyone's familiar with. What else can we say about this space? Well, let me just immediately identify from this description. We know what the cotangent bundle to pic 0, or in fact to the whole group. The cotangent bundle to pic 0, well, this is a group. The cotangent spaces are identified at any point. At any particular point L, the cotangent space is naturally identified with the space of holomorphic one forms from this description. OK, so I mean, you can also get this maybe. One way to derive this would be to first look at what is the tangent space to the Picard group, to think what are the first order deformations of a line bundle. And we can calculate this in different ways by some kind of cohomology group. For example, in Dolbeau language, this would be H01 of X. And so this description comes from dualizing that. So OK, so this is the Jacobian. And what do we know about the Jacobian? The first thing we learned, I guess, in the 18-something, long time ago, Abel and Jacobi told us several things about it. First of all, there's Abel-Jacobi map, which is I'm going to fix a point, x naught, a base point in my Riemann surface, and then I have a map from x to the Jacobian, which is just given by integration. So given any point x, I go to integration from x naught to x. This is a functional on one forms, and it's well defined up to the homology. So that's an element of that quotient space. It's well defined. OK, so this gives me a map. Now, what can we say about this map? There's a lot of nice features about this map. One thing it does, if we look at what this map does in pi 1, so we have a map from this Riemann surface to the Jacobian. And well, if we take pi 1 of x, say at some base point, and look at its abelianization, so the abelianization of pi 1 is h1 of x z, and we notice that that's the same as the fundamental group of this torus. So this torus is a vector space model lattice. That lattice is naturally identified with pi 1 of the Jacobian of x. And this map, so the Abel-Jacobi map induces an isomorphism on pi 1, abelianized to pi 1 of the Jacobian. So what does this tell us? This tells us something very nice, which is maybe a kind of a baby version of class field theory. So geometric class field theory, which is going to be a precursor to the geometric Langlands correspondence, in the kind of the simplest version of it, says the following. What does abelianized pi 1 tell us? Abelianized pi 1 controls abelian covers of x. On the other hand, pi 1 controls covers of the Jacobian, so they're going to be the same. So that's the kind of the first version, is that abelian covers of x are induced by, and abelian covers, if you like, of the Jacobian, which are all the covers, correspond. And in fact, they correspond very explicitly. If I give you a abelian cover of the Jacobian, you just restrict it to the image of the Abel-Jacobi map. And that gives you an abelian cover of x. So that's kind of the first version of geometric class field theory. This is kind of the kind of first, I guess, Langlandsy statement that we're going to see. So this may be not so exciting. Let's try to make it, jazz it up a little bit. Instead of looking at, say, finite abelian covers, I can look at something a little more complicated. I'm going to look at flat line bundles on X. So what's a flat line bundle on X? Well, you can think of it in many ways, but right now I want to think of it in terms of its monodromy. The monodromy, if I have a line bundle with a flat connection, it's completely determined by, for every path in X, I get a monodromy, which is a number in C star. So we get a homomorphism from pi 1 of X to C star, but this factors through the abelianization of pi 1 of X. Because of this abelian, but the abelianization of pi 1 of x is pi 1 of the Jacobian. And so we get that flat line bundles on X are the same thing as flat line bundles on the Jacobian of X. And again, this is induced, so both of them are described by the same exact monodromy data. And again, this is induced by pullback from the Abel-Jacobi map. Just restrict your flat line bundle to the image of the Abel-Jacobi map. OK, so this is the basic content of geometric class field theory. And now I want to try to say the same things in very complicated ways. So what are going to be the complicated ways? And I'd like to bring in the kind of stuff we talked about yesterday. So how do we do this? What I'd like to say is that this correspondence is just kind of a piece of a Fourier transform. And so I want to extend this to some kind of Fourier transform, a Fourier transform on the Jacobian. So So how is that going to work? So this is maybe a review, kind of crash review of some of the things from yesterday. So the first thing, so maybe I don't know how long this will keep up. Let me try to have a parallel boards. So remember that last time we had for A an abelian variety, we looked at its dual abelian variety, and we had this Fourier-Mukai transform, which was an isomorphism of function spaces from O modules on A to O modules on A dual. So this was our Fourier-Mukai transform, which was characterized by the fact that inside of here you have line bundles, and the points of A dual are given by these. So here it said you have line bundles of degree 0, or in particular these characters, and these correspond to points of A dual. So these correspond to skyscraper sheaves here. So this is kind of the main feature of the Fourier-Mukai transform. Well, one of the nice features. So what happens here, so if you look at the Jacobian of X, this is an abelian variety, but luckily it's actually canonically self-dual. So it's isomorphic to its dual. This is given by this principal polarization of the Jacobian given by the theta divisor. So this is a self-dual abelian variety, so we get a Fourier transform that exchanges O modules on the Jacobian with themselves. Okay, so that's just applying this. So now, what else can we do? This so far doesn't seem to have anything to do with what's on that board. The next thing we can do is we can look at if we have, so let's do a kind of silly families version. So what's going to be the families version of the Fourier-Mukai transform? I'm going to have, suppose I have a variety A over some base B. So B is going to be some simple, say, a vector space. It's going to be the base. And this is a family of abelian varieties. Family of abelian varieties. What can I do? I can look at fiber-wise dual. So each fiber is an abelian variety. I can look at characters on each fiber. So I can, or if you'd like, if you think of this as a family of complex tori, I could just take the family of dual tori. So this is the collection of dual abelian varieties. So this is the dual family. And it's, if you think of how the Fourier-Mukai transform, you can just do it in families. And you get equivalence from derived category A, O, derived category of A, check O, which is just fiber-wise Fourier-Mukai transform. Okay, great. So what I'd like to do is have a version of that for the Jacobian. And to do this, I'm going to have a really silly family. And what's my family? I'm going to look at the cotangent bundle of the Jacobian again. Now, the cotangent bundle of the Jacobian we decided that cotangents fibers every place are the same. So this is isomorphic to the Jacobian of X cross the cotangent space at any point, which is the space of holomorphic one forms. So let me then say, let me call A the cotangent bundle of the Jacobian. And I'm going to think of this as a family of abelian varieties over some base. Well, what's a base? Well, there's an obvious projection here. Just project onto the second factor. So there's a base B, which is just the vector space of holomorphic one forms. So there's a map from cotangent bundle of the Jacobian to just the second factor, which is, I'll call Hitchin's integrable system. So this is the first instance of the integrable system of Hitchin, which we'll see in the non-abelian setting a little later. So, but in this abelian context, it's just a projection onto a factor. Yeah, so when I say family, it should be some reasonable family, or you'll have to think a little more carefully about what you mean by this derived equivalence. OK, so, and what's my dual family? Well, this is a silly family. It's just all the fibers are the same. so the dual is also the same. A check is also isomorphic to T star of the Jacobian. So we get a family's version of this Fourier Mukai that if you take the derived category of T star of the Jacobian, then it has a Fourier Mukai autoequivalence. OK, so of course we could have done this with any abelian variety. The only point that's special here is that the two sides are the same. For any abelian variety, we could take its cotangent bundle and project onto the second. It's going to be a product. We can project onto the second factor. And so we get this kind of, same kind of picture.
Is this autoequivalence an involution? You do it twice,
you get the identity up to some shift and sign. I mean, like the usual Fourier transform, there's some correction. But the same kind of. Yeah, so sorry, this, yeah, that's a good point. My notation will always be, this is going to be the notation throughout the week. I have D of a space O means O modules on that space. So this is O modules on T star of the Jacobian. So maybe I'll just draw some kind of caricature of this story. I have this, this is supposed to be the Jacobian. And so I have this T star of the Jacobian is Jacobian cross a vector space. And I'm thinking of the projection onto the second factor. So that's supposed to symbolize T star of the Jacobian. On the other side, I have the same space. But what I want to emphasize, this map, of course, is not the identity. I mean, this is not a silly map. It's a Fourier transform. So in particular, if you take, so somewhere in this Jacobian is the point 0, is the origin of the group law. So if you take the origin of the group law on any fiber, it gets Fourier transformed. This is where color might be useful. So the origin of the group law gets Fourier transformed to the structure sheaf of a fiber. So if you take the origin in any particular fiber, so we have this kind of slice. We have a slice of this projection, which is just take 0 times cotangent fiber. So cotangent fiber at 0. And these points exactly correspond to structure sheaves of fibers. So these correspond to structure sheaves of fibers. So that's kind of a caricature of this transform. So it's certainly not a trivial map. It's probably not so exciting, but let's see what we can do with it. So, well, maybe let me also note why am I using the words integrable system to denote this map? Let's notice that the total space is symplectic. It's a cotangent bundle, and the fibers are, well, they're this translated versions of the zero section. They're Lagrangians. So it's a Lagrangian fibration of a symplectic manifold. In fact, with Lagrangian tori as the fibers. So that's some version of what an integrable system is. Let me also note that this map is proper. So another nice fact about this, that if I look at functions on the cotangent bundle of the Jacobian, let's suppose we actually looked at what are usual, not some fancy notion, what usual polynomial functions. Well, there are no non-constant fibers, functions on each fiber. So these functions all come by pullback from the base. So these are just the same as functions on the Hitchin base space, on the space of one forms. So this is, so in other words, and these, so I can call these, this is the abelian version of, we'll call these the Hitchin Hamiltonians. These functions, when you pull back, they all Poisson commute, and they define some commuting flows that are translation along the fiber, if you're familiar with integrable systems picture. So, OK, and what is this? Let me just point out that functions on this base is the same. What is the base? The base is h naught of omega 1. Polynomial functions on a vector space are just the symmetric algebra of the dual. So this is the symmetric algebra symmetric algebra of the tangent space at any point to the Jacobian. So that's going to be a useful identification. OK, so this is the story. But now it still seems to have nothing to do with what I'm about to erase. So how does this have to do with flat line bundles? So far, there are no flat line bundles. What I'd like to do now is to deform this picture. So if you will recall from last time, if we look at functions on the cotangent bundle of some space, have a natural deformation, which is differential operators on that space. We put in this h bar parameter, and we think of differential operators in space as deformation as functions of the cotangent bundle. So that means that if we look at this derived category of T star of the Jacobian, it has a natural deformation, nice flat deformation. And where does that go? Well, instead of looking at O modules on T star of the Jacobian, we'll look at modules for the deformed ring, which is the ring of differential operators. So this is some notation that didn't make it to yesterday. So we're going to look not at the Jacobian, not at T star of the Jacobian, but the Jacobian itself. We look at D modules there. So this is actually maybe the main star of the week. This is the derived category of D modules on the Jacobian of X. So again, so this is, as I discussed yesterday, this is supposed to, the D module we think of as some kind of function space. Of course, we said the same of O modules. These are both different kind of function spaces. You notice that this function space is somehow double the size. It somehow looks more like functions on T star of X. But in any case, I'm going to proceed to think of this as some kind of function space, and it's given in the same way. It's given by some kind of complexes of D modules up to quasi-isomorphism and some technical stuff we'll omit. So this is our main star. We're going to look at the derived category of D modules on the Jacobian. So now you can ask, what happens to the Fourier transform here? So I've deformed one side of this. So a natural guess might be that, that the same thing happens to the other side. And that turns out to be false. So let's try to think what should happen to the other side. And so to do this, I want to maybe retreat for a second to a context of an abelian variety and think what should happen if you try to do, what would happen if we tried to do a Fourier transform, a version of the Fourier-Mukai transform, not for O modules, but for D modules. What should that be? Well, this is not such a strange thing to do. What should we do? To an abelian variety A, we should look at the collection of flat characters of A. So before, to do the Fourier transform, we looked at characters of A. So these were line bundles with this multiplicative property. So now we're looking at D modules. What are examples of D modules? These are flat line bundles. So these are flat line bundles, not just line bundles, but now line bundles with a flat connection. And with this multiplicativity, with this character property, you pull back, you are identified with the product. So this is the character property, but now everything is compatible with a flat connection. So we're just going to try to do the exact same story, do the Fourier transform, just replacing line bundles by flat line bundles. And everything works perfectly. So that's the story. So first of all, what is the space? For A, the space of characters was just the dual abelian variety. Now this maps to the dual abelian variety of A. I just forget the connection. Right? These are line bundles with some connection data and some character property. I could just forget the fact that everything's compatible with the connection. I get a map to the dual abelian variety. What are the fibers of this map? Well, the fibers of this map are exactly connections. If you take one of these line bundles and you try to put a connection on it, what are connections on a line bundle given by? They're given by one forms. So the fibers of this map look like one form. So we'll give this guy a name A natural. And so there's this what is A natural? It's an affine bundle over A check, modeled on I don't know. So let's say model. So it's an affine bundle. It's not a vector bundle. But it's an affine bundle modeled on the vector space H naught of A one forms. The difference between two connections on A is going to be given by a one form. So this is the space A natural. So notice that this is also the cotangent space to A at some point, at any point. So we have an affine bundle modeled on this cotangent bundle. So let's return to the comfort of Jacobians. And so in the case of a Jacobian, what do we get? Well, everything is self-dual. And so we get the space Jacobian natural mapping to the Jacobian. So this is the space of flat line bundles on the Jacobian. So I omitted the word character. So the same thing that happened last time, we discovered that these characters of an abelian variety are the same thing as just line bundles of degree 0. So we can forget about the connection and realize that as a space, this is just a space of flat line bundles on the Jacobian, which happens to also be the space of flat line bundles on X, on the Riemann surface. So that's what this space is that we're talking about. It's just a space of line bundles with flat connection on X. So I'm going to give it a different name. I'm going to call it connections GL for GL1 on X. It's a space of line bundles, GL1 bundles with a flat connection on the Riemann surface X. Okay. Is the notation clear? Okay, so now what does the Fourier-Mukai transform do? So the Fourier-Mukai transform extends the same way. So the usual Fourier-Mukai transform said that you can take any sheaf on A and write it as an integral of characters. So now the same statement will work. You take any sheaf with a flat connection and write it as an integral of flat characters. So yes. Yeah, the Chern class is given by the curvature.
So this map is actually...
This map is surjective, and it's just an affine fibration. And in fact, thank you, I should point out that this is an affine bundle which is modeled on the cotangent bundle to the Jacobian. So in fact, it's a deformation of cotangent bundle of the Jacobian. Cotangent bundle of the Jacobian looks like space of line bundles without connection. A one form looks like connection in a line bundle, but there's no canonical identification. So this space is actually a nice deformation, as any affine bundle is a deformation of the corresponding vector bundle. So this is a deformation of the cotangent bundle of the Jacobian. But now it's a deformation it's a nice variety, which is a deformation. In fact, it's a nice symplectic variety. And so now we can guess what's going to happen to this picture when we deform. This side, we deform to D modules on the Jacobian. But when we try to do Fourier transform for D modules, what we find is that the natural parameter space is not the same thing. It becomes this space Jack natural. So now let me state this as a theorem. Maybe I want to keep this. So there's a theorem due to Lemon and Rothstein, which says, in fact, this works for any abelian variety, but let me state it for the Jacobian, says that the derived category of D modules on the Jacobian is equivalent to the derived category now of this Jack natural O. So first of all, just to see kind of structurally why is this the right kind of statement, both of these sides are deformed versions of the cotangent bundle of the Jacobian. They have the same size. Now, it looks kind of strange because one side is a non-commutative deformation. The other side is a commutative but affine deformation. So we see that under these derived equivalences, different kinds of deformations get switched. But this is why, but at least both of these you should think of as some kind of versions of the cotangent bundle. Here it's been quantized, and here it's been deformed. So if you look at this picture, what happens now is that the left-hand side kind of becomes fuzzy, and the right-hand side no longer projects onto the Jacobian. It's an affine bundle without a section. But that's sort of what this looks like. And what does it mean? It means the same thing as the usual Fourier transform. It means that anything can be written in terms as an integral of characters, as a linear combination of characters. What this says is that i.e. any D module, so in other words, any sheaf with flat connection, is a linear combination, or an integral is an integral of flat characters. So this transform has the property that if I give you a line bundle with a flat connection, thought of as a D module on the Jacobian, it goes to the skyscraper at the corresponding flat line bundle, thought of as a point of Jack natural. So that's a kind of Fourier property of it. And if you want to ask what the map is actually the same map. If you'd like, you can think of D modules as sheaves on the Jacobian with extra structure. In the same way, you can think of these things by projecting down. These are sheaves on the Jacobian with some extra structure. So the actual functor is given by the same Fourier transform that we had yesterday. You're just keeping track of what happens to a flat connection under that map. Okay. So, so this is the main point, that these flat line bundles, these flat characters, exactly go to skyscrapers, or if you like, points. So it's the same kind of Fourier transform.
You are applying this high fiber-wise to this vibration.
Right.
And then this was also deformed.
Right. The vibration dies. It does not persist under deformation. But the claim is that this equivalence persists. So what happens is I take this equivalence fiber-wise, and I deform this side in a non-commutative way, and I deform the equivalence, and this side gets deformed in a commutative way. As becomes an O modules on an affine bundle.
So after deformation, I don't have this vibration.
No, you don't have this vibration picture. The vibration is kind of a classical limit. We'll use that terminology again, but it's some kind of degenerate version of this. Okay, so this is, so maybe it's worth pointing out again that this is the same. This is now just a change of notation. This is O modules on the space of line bundles with connection on X. So now what have we done? We've taken this, what used to be here, we've taken this very simple statement that flat line bundles on X and on the Jacobian correspond, and we've said it in a very complicated way. If I give you a flat line bundle, so let's say L nabla is a flat line bundle on my Riemann surface on X, that's the same thing as a flat line bundle on the Jacobian. In other words, it gives me a point. Well, actually, maybe I'd rather just say that this defines a skyscraper sheaf, O of L nabla, which lives in this derived category of connections, GL1 O. And what we've assigned to it under this Fourier transform, so to any flat line bundle on X, we assign by this transform a flat line bundle on the Jacobian, which is in fact a flat character. So the flat line bundles on X give you these flat characters in Jacobian, which we already knew. But this actually says that these things span, that any sheaf on the Jacobian, any D module on the Jacobian can be decomposed in terms of flat line bundles on the Riemann surface. This is going to be the geometric Langlands correspondence in the non-abelian case. So when we get to geometric Langlands, it'll be exactly this statement said in a non-abelian way. Okay, so one maybe it's worth pointing out that this transform, which might look a little abstract, is incredibly silly, maybe. It's incredibly, you can write it down very explicitly on some piece of this. So maybe let me just point out that we had this picture. Luckily, it's even there. So we have this picture before deforming. And we had this particular slice here. And we knew, to points on this slice, we knew exactly what we're assigning. To points on this slice, we just assign structure sheaf of the corresponding fiber. So this picture has a nice quantization. It's called quantization of Hitchin's Hamiltonians. And how does that work? We're going to say, inside of this big world, connections on the Riemann surface, inside of this space of connections, there's a particular piece that I understand very well, which is I look at connections on the trivial bundle, line bundle. So this is what this slice was. We looked at the trivial bundle and looked at the slice here. So what is connections on the trivial bundle? Connections on the trivial bundle. So this is connection on the trivial bundle is some piece in here. Well, it's a fiber over the trivial bundle. But a connection on the trivial bundle really is the same thing as a one form. So this particular fiber I could really identify with a one form. And so what are we saying? So to any connection on the trivial bundle, we have a one form. So we have this. So we have functions, and so in particular, if you like, functions on this slide. This equal is inappropriately. There we go. So that's the space of one forms. So the space of one forms are the same as connections on the trivial bundle. So in other words, that even after we deform, so let me now take this picture and deform it. So this side, I'll write it like this. It's gotten quantized. So this is kind of the D module side. And this fibration no longer exists. So this is just some fuzzy picture here. But on the other side, we have we've deformed. So we no longer have a projection. But on the other side, we've taken the Jacobian. And here I'm going to draw the Jacobian natural, the space of connections. And that's some kind of affine bundle. Some kind of affine bundle with fibers look like the space of one form. But the fiber over the trivial line bundle is canonically identified with the space of one forms. So inside of this space of line bundles with connection, I have a slice that I understand, a Lagrangian slice. And functions on that slice are exactly this algebra we have here. I mean, the slice is isomorphic to the base. So this is function on the slice. And let me note, what is this thing? Symmetric algebra of vector fields on the Jacobian. These are exactly constant coefficient differential operators. So this is the same as, these are just constant. So I think of the tangent space at one point as being constant vector field, invariant vector field. And these are just the translation invariant, or if you'd like, constant coefficient differential operators. But actually, on an abelian variety, any global differential operator is constant coefficient. If you try to look at a global section of the differential operators, it has to be constant coefficient because the tangent bundle is trivial. So functions on the slice are actually global sections of the sheaf of differential operators. So maybe I won't elaborate on this now. We'll return to this later. But this immediately tells you how to assign. So we know how to construct this Fourier transform on this particular piece. Because we know that that functions on the space of connections on the trivial bundle are the same thing as global differential operators. So if I give you a module over functions here, I can construct out of it a module over differential operators just by imposing these constraints. So maybe I should write.
This base is only Jacobian, right?
Sorry?
The base is now only Jacobian, not the
T naught is the tangent space of the Jacobian. Yeah.
You're applying it only to the Jacobian.
No, this is just a statement that the ring of functions on this base is the same as the ring of symmetric functions of the dual space. B is one forms, it's the cotangent space, so its functions on the base are the symmetric of the dual, which is the tangent space. And now I'm identifying this tangent space with global differential operators. So let me just maybe write this. So this is going to be the abelian version of Beilinson and Drinfeld's quantization of the Hitchin system. So so if you give me M is a module over functions O of the space of connections on the trivial bundle, in other words, something in here, then I can assign to it a D module on the Jacobian, which is I just take the differential operators on the Jacobian and I tensor it with M over global differential operators, using the identification that this is the ring of global differential operators. So in other words, I take D and just quotient it out by some ideal, which is the same ideal that defines my module. So that's what this Fourier transform is doing on this particular slice. It's something you can just write down explicitly. Okay. So, all right. Other questions about this? Okay. So this is the Fourier picture for geometric class field theory. What I'd like to do now is go to the.
If you could just summarize that. You say this.
This, right.
Exactly what is that?
So there's yeah, that's yeah, sure. So there's two statements. Well, there's several pieces of data. One is that D modules on the Jacobian correspond to O modules on the space of line bundles with a flat connection on the Riemann surface.
Does that mean derived categories?
This means derived categories. And in such a way that skyscrapers, points in here, which are a line bundle with a flat connection, take a skyscraper here, these correspond to very special ones, which has this character or eigensheaf property. That we said the character property can be set in this other way, which we called an eigensheaf. It's just a silly way of writing the same thing. So this is the statement. And moreover, there was a statement that you can write it very explicitly on a small piece, on a slice. You can write this just in terms of global differential operators. And moreover, there was a statement that this was a quantization, a deformation of Hitchin's integrable system of this, it's quantization of this duality. There was a silly duality on cotangent bundle of Jacobian, and we deformed one side, and the other side got deformed too. So what I'd like to do is explain all of this now in the non-abelian setting. Okay, so now we get to moduli spaces of bundles. So what's going to be our context? So we're going to start with G. Is going to be a reductive and complex algebraic group, reductive group. So this means we can, for most of the time, we'll just think of GLNC. But if you'd like, we could also put in SLNC or your favorite complex Lie group, etc. So these are, so this is what we look at. And so then we have a notion of principal G bundle on a Riemann surface X. So that's something that maps to X with a simply transitive action of G along the fibers. So this is an algebraic variety mapping to X with an action of G that's simply transitive along the fibers. And so, for example, for G equals GLN, these things are in bijection with vector bundles. So if V is a rank n vector bundle, this is the same thing as a principal GLN bundle. Principal GLN bundle. Via the assignment, I look at all frames. So all bases of fibers of V. Bases of fibers of V are acted on simply transitively by GLN. So we can think of a principal G bundle as, in the case of, mostly we'll just be talking about vector bundles. So this is rank n vector bundles on a Riemann surface. So, for example, if G is GL1, GL1, this is the same thing as what we've been studying. These are holomorphic line bundles. Okay. So what do we want to do with this? Well, for GL1, what we did was we looked at the Picard group. And we did a kind of Fourier theory on the Picard group. So what are we going to do now? We need to replace the Picard group by a beautiful space called Bund G of x, which is the moduli space of G bundles on X. So I'm going to look at all G bundles on X, and I'm going to try to parameterize them. And we're going to try to make a nice space out of this. So we have to think, what exactly does that mean? Well, we want it in, so how do we, so for example, maybe I should just have the notation. Bun n of X is the moduli space of vector bundles of rank n on X. So the use of the word space here might be a little interesting. So what kind of, I claim that this is the same kind of algebraic space that we've been dealing with. So this is something that's covered by affine varieties, has a nice charts given by affine varieties, and with some gluing maps, where the gluing maps might be complicated. So, so why am I allowed to think of G bundles as a space? The point is that we have a notion of a family, of a holomorphic flat like family of G bundles. We know how to vary G bundles in a nice way. So we can try to look for a way to parameterize all G bundles on a Riemann surface. And in fact, you can Bund G of x can be covered by some union of affine varieties. And how do you find this variety? So if you give me a particular, say, if you give me a particular vector bundle V, then for any V, some neighborhood of V, of V can be parametrized as quotients of some fixed vector bundle, some fixed higher rank vector bundle of some fixed. So what does this mean? Open set to any deformation of V, you can realize in terms of some nice family, which is just take a fixed vector bundle and look at all of its quotients, which are rank n vector bundles. So this is why this is a nice space. So for any because quotients of a fixed bundle form a nice variety, and any bundle has an open piece covering it that looks like that. And moreover, this is not just a space, this is actually a smooth space. This has all the nice property of a smooth variety that I can cover it with smooth charts, smooth varieties. So these space of quotients are smooth, and the transition maps are smooth, and the projection maps are smooth. So from all practical purposes, this is a smooth variety. So there's, or many practical purposes. So I should say the word at some point. And so really what this is what's known as smooth algebraic stack. But I'm going to treat it just as a variety. For the purposes of what we've been doing, we talked about looking at O modules or D modules, these kind of function theories. They are done purely locally in terms of some atlas. And here we have very nice atlases, and we're going to think of this just as a nice smooth algebraic variety.
When you say the quotient vector bundle, I mean, this means we have a sub-vector bundle, and we're taking the quotient.
Right. So they're all, you look at the space of all n-dimensional quotients of some fixed high-rank bundle.
Suppose that two of these quotients for different sub-vector bundles
Right.
happen to be isomorphic.
Which will certainly happen.
Do you identify the two?
Yes. So I'm not saying this is a one-to-one. This is not an open embedding.
I see.
Right. So that's why the word stack comes in. that these are not open pieces. They map onto open pieces, and the fibers are acted on by some big GL group. So it's a quotient.
It's the Grassmannian
It's-
of sub-vector.
That's right. That's right. It's some quotient of it's parametrized. The space is locally looks like a quotient of a Grassmannian by some GLN, K, GLK. But so that's action of a smooth action of action of a smooth group on a smooth space. And so for all practical purposes, the quotient is smooth. For the categorical, all practical categorical purposes, which is what we'll be doing, the quotient is smooth. So that's why I'm kind of, the point is that the relations here, the gluing laws, these are sort of more complicated groupoids. These are sort of not, this is the gluing laws for how to glue these opens. These are groupoids with some stabilizers, which is.
You're saying this is not just a classical algebraic.
That's right.
This is true for X curve.
For X a curve, yeah, everything here is going to be for curves, yeah. The smoothness, I mean, the other parts are probably fine, but the smoothness is certainly something about being a curve. Okay.
So is this higher dimensional vector bundle easy to describe?
Yeah, I mean, if you take a vector bundle and you tensor it by a very ample line bundle, then it'll be generated by global sections. And then you look at the trivial bundle with fiber those global sections and appropriately twisted, and that'll give your bundle that'll surject onto your bundle. So that's how you parameterize it. But for the point is that there's not one twist that'll work for all vector bundles. So you need to this gives you a bunch of open charts, but there's sort of many, many of these. So any particular bundle, you can fix some fixed rank. Any neighborhood of any particular bundle will be given by some fixed quotients of some fixed rank thing, but the further out you go in this space. So maybe if later, if there's time, I can draw some pictures of what these spaces look like. But okay. So it's a good exercise to see what this space looks like in the case of just P1. And in the case of P1, the set of bundles is a discrete set, but the kind of structure, the geometric structure on them, is non-discrete. Okay, so maybe we'll accept this as another black box, and the main point is that this is going to give, if you'd like, a good non-commutative space from the point of view we were talking yesterday. We can talk about these categories of sheaves just the same as in the case of a variety, and so that's going to be our main purpose. But let's say something a little more geometric. Which is one thing we can ask about this space is what is the cotangent bundle to Ben-Zvi? So the first problem, I guess this is sort of already a slight problem. This is a more complicated kind of object than the Jacobian. But the real issue and the real difficulty in what we'll be doing is that this is not in any reasonable sense not a group, unlike the Picard. In the rank 1 case, you can take the tensor product of two line bundles and you get a line bundle. You can't take the tensor product of two G bundles. So this is not a group, and what we're going to try to figure out is how to come up with some kind of Fourier theory on this space, even though it's not a group. And for that, we're going to have to see what are some of the symmetries of this. So the one geometric question we can ask is, what does the cotangent bundle of this space Ben-Zvi look like? So how do we do this? So maybe I'll just state the answer and then can say how you would come up with this. So if I give you a G bundle on X, well, in the case of line bundle, remember that the cotangent was given by just one forms on the Riemann surface. So what happens here? It's not a group, so our answer is going to depend on which point we're at. So we look at the cotangent bundle of Ben-Zvi of X, and the claim is that this is the space of holomorphic sections of one forms, but twisted. These are going to be matrix valued one forms twisted by the adjoint bundle of P. So in the GLN notation, maybe in the case of GLN, if this is just a vector bundle, this is just a way of saying H naught of X with coefficients in endomorphisms of my vector bundle tensor one forms. So it's just matrix-valued one-forms on my vector bundle. So this is the cotangent fiber at any particular point. And remember, I'm treating this as a smooth variety. So it's going to have some nice cotangent bundles, some nice definition of a cotangent space, at least. And so these things we're going to call Higgs fields. Higgs fields on P or on V. So V is going to be my notation for the corresponding vector bundle. So, these Higgs fields are, so in other words, if you'd like, have this maybe introduce some notation. Higgs Gx is cotangent bundle of Bun-G X. This is the total space of the cotangent bundle, is the moduli space of these Higgs fields. So this is the moduli space of pairs of P and eta, where eta is a Higgs field on P. One forms. So this is the moduli space of Higgs bundles, and that's the cotangent bundle. So notice in the case of a line bundle, endomorphisms of a line bundle, this are just scalars, so this term goes away. So that's why we had h naught of x with coefficients in one forms. Okay, so how would you deduce this? You can deduce this by thinking what the tangent space is. And the tangent space is given by first order deformations. So what are first order deformations of a vector bundle? And you can do this, again, either in a check or a Dolbeau picture. You can either try to twist the transition functions of a vector bundle on overlaps, or you could try to add some part to the del bar operator on your holomorphic vector bundle. But in either way, you get that the tangent space, so this is maybe an aside, the tangent space is given by H01 of x with coefficients in add p. So this is what happens when you take the gluing, infinitesimally try to change the gluing data that's defining the bundle. And you get this as calculation tangent space, and the cotangent space comes from state duality. So this is, I would like to think of the tangent space. So maybe I want to make one more note, is that this space of Higgs bundles, these Higgs fields look a lot like connections. So these eta in h naught of x, these adjoint valued one forms, they look like connections on P. More precisely, if I take two connections on P, the difference between them is given by such a thing. So if nabla 1 and nabla 2 are two connections, their difference between them is an eta, is a Higgs field. So is the difference between two connections. So the space of connections is an affine bundle. So this suggests we can look at something else. We can look at the space, which I'll denote con G of x, which is the space of G bundles with holomorphic connections. So these are G bundles, and again, everything I'm talking about are holomorphic. So these are holomorphic connections. And what we find is this is an affine bundle. This is an affine bundle modeled on the cotangent bundle of Bun-G. For the fiber over a fixed P, these are the connections on a fixed P have their differences are given by eta, where eta is in the corresponding cotangent bundle. So, okay, so maybe we'll continue with this afterwards.